Alrighty, welcome to the last lesson of chapter 10. Topic here is using inference to make a decision. And it is a very important use of inference, especially in things like manufacturing, in drug approval, things like that. So it brings up a couple of interesting new ideas, though. Okay, so in manufacturing, you could be doing something called acceptance sampling. Okay, so the idea here is, let's say you're in quality control for a manufacturing plant. You randomly sample your whatever it is you're making off the assembly line. And then you have to decide, hey, are my machines in calibration? Should we continue the production run? Or does this sample tell me my machines are out of calibration and I need to shut down the production run and recalibrate, right? That's the idea of what's happening here. So we're gonna use the significance test to make one of those two decisions. I either keep the production run going or I shut it down and recalibrate. Up until now, we've had the luxury of saying, well, we just don't have enough evidence, and then leave it at that. Well, when I'm running a manufacturing plant, it's either keep it running or shut it down. I can't just kind of say, well, not enough evidence. Well, if I keep it running, then I'm basically accepting the null hypothesis, right? That it's manufacturing items that are acceptable, right? If I shut it down, then I'm rejecting the null hypothesis. So that's the idea of acceptance sampling. So when you're in a situation where you have to pick, that's considered to be acceptance sampling, okay? Now, again, sometimes you're not in a situation where you have to pick, right? You're more of a researcher doing more theoretical type work, then you're allowed to just say, well, I don't have enough evidence, and leave it at that, right? But if you're trying to say, hey, this drug gets approval or doesn't get approval, I shut down my production facility and recalibrate, or I don't, right? In those situations, there's no kind of middle ground. All right, so if you are forced to accept either the null hypothesis or the alternative, right? If you're forced to make a pick, errors are going to occur, right? So we have two errors, type 1 error and type 2 error. Okay, so here's the four things that can happen. It can be that in reality our null hypothesis is true, okay, but we reject it. Okay, that is called a type 1 error. We've made a mistake. Our null hypothesis is true, but we're rejecting it and accepting the alternative. Okay, and that's going to happen with a probability of alpha, right? Because let's say alpha is 5%. Well, random chance, 5% of the time is going to put you in that rejection region, even though H naught is true. That's just the definition of alpha. So that's a piece of cake, easy. Okay, now if H naught is true and I'm again forced to make a pick and I accept H naught, then I've made a correct decision, and the probability of that will simply be the complement, right? 1 minus alpha. Again, very easy to calculate. Now, when the null hypothesis is false, again, two things could happen. I reject it, accepting the alternative, which again would be a correct decision, a good place to be. We're going to call that the power. That's the power of the test against an alternative, okay? Or it could be that the null hypothesis is false, but I accept it anyway, okay? So that is another error. It's another mistake. We're calling that one a type 2 error. Okay, the good news is these are, of course, complementary, right? Because if H naught is false, those are the only two outcomes if you're forced to pick, right? One's a correct decision and one is an incorrect decision, and they're complementary. The bad news is the calculation here is a little bit complicated for a lot of students. A lot of students would say it's the most complicated calculation of the year. So anyway, we'll get to that in a minute. Okay, so here it is in words. So type 1 error, we're rejecting a null hypothesis when in fact the null hypothesis is true. Okay. A type 2 error is accepting the null hypothesis when in fact the null hypothesis is false. Okay, so those are the two types of errors, and here we can see the two types of errors. Okay. And by the way, on the test, you will be asked, in this situation, an error was made, is it a type 1 or a type 2 error? Or we might say, please describe a type 1 error in this situation, or please describe what a type 2 error would be in this situation. So make sure you're able to do that. All right, so here's the calculations. Again, the type 1 error is a no-brainer. It's simply alpha. Whatever you're using as your alpha, there's the probability of making a type 1 error. And of course, it could be a one-tail, right tail, or a left tail. Or if it's a two-tail test, then your alpha, of course, is divided equally. Now, the type 2 error is a little bit trickier. So we will be doing an example in a bit. Okay. And again, it's the probability of accepting a null hypothesis when it's not true, when the alternative is true. So this graph right here is super useful. Okay. So we have two normal curves. Okay. The normal curve on the left is the normal curve under the null hypothesis, right? Null, nothing, right? The mean's right there. Now, sometimes I'll get an extreme sample, even though the null hypothesis is true. And when I land out there on the tail, I will reject the null hypothesis incorrectly, right? So that's an error right there, and it'll have the probability of alpha. Okay. Now, this curve on the right is the curve that you would be working with if the null hypothesis were actually false. Okay, so here's an alternative normal distribution. Okay, now when this alternative normal distribution is true and you land anywhere over here, right, from here over, you're going to correctly say, the null hypothesis curve is false. Okay. But sometimes, right, even though this is the true curve, you will land over here due to random chance. And when that happens, you will be thinking that you're on this curve, even though you're not, right? So that would be when the type 2 error occurs. When the data came from this curve, but because of random chance, you ended up on the tail of this curve, so you thought you were over here in the null hypothesis curve, okay? All right. So here's the definition of power. Okay. It's the probability that your fixed level alpha significance test will reject the null hypothesis when a particular alternative value of the parameter is true. Okay. So that's what this second curve is, right? Here's the alternative value. The alternative, in this case, mu, over here, okay? And we have to be given that in order to do the calculation. Without that information, then we can't figure out the probability of landing in this beta region, okay? And of course, the power is equal to 1 minus type 2 error. They're complementary. Or you could say type 2 error is equal to 1 minus power, right? You just have to calculate one of them, and then you can use the complement to get the other. All right, so ways to increase your power. Because, of course, we want to make correct decisions. That's a good thing, right? We want to have a high power, okay? But here's the downside. To increase your power, right, what I could do is I could move this alpha line, right? I could move the alpha line that way, right? If I move the alpha line that way, I increase my power, right? Because I'll have less beta region. But the bad news is I now have more type 1 error, right? So there's a trade-off, right? If I increase my type 1 error, it'll decrease my type 2 error, and vice versa. But they're both errors, so they kind of fight each other there. Okay, so usually the way to increase power without sacrificing type 1 error would be increase your sample size. right? Because that creates less variation. So in other words, we'll make both of these curves more narrow by increasing n, and that'll give them less overlap, which shrinks both of those errors. In theory, if you could decrease your sigma, right? Again, that makes the curves more narrow. Oftentimes you cannot do anything about sigma because it's a parameter, but sometimes you might be able to get, in manufacturing a more accurate machinery or something along those lines. And then the last way to increase power is to try to take this curve on the right and move it further away from the null hypothesis, right? The more you can spread these curves out, the less overlap they would have. Again, a lot of times that's beyond your control. Okay, so oftentimes the only one that's actually in your control is that one right there, sample size, oftentimes. But in theory, the other three would also be able to increase your power. All right, so let's try a problem. Let's say you are in manufacturing, okay? And you make ball bearings. Very useful product. Now, while you're making ball bearings, right, at some point, your machinery will get out of calibration, right? So every so often, you're going to do samples from the production run and measure them and inspect them and decide, okay, things are fine, keep it running, or whoa, shut down the machinery, we're out of calibration, we need to recalibrate everything, right? In other words, doing acceptance sampling. All right, so let's say the diameter of the ball bearings you're producing is meant to be 2 centimeters, okay? Now, you're going to be sampling from your production run, and you've decided that your machinery has a sigma of 0.01 centimeters, okay? You're going to sample 5 ball bearings from the production run, and you're going to use an alpha of 5% to determine if you should shut things down or not, okay? Now, there's one more piece of the puzzle. You need that alternative curve. Where's the alternative curve located? So we're going to say, if my ball bearings have a mean diameter of 2.015 or more, we're going to call them defective. We won't be able to sell them, use them, whatever, okay? So that's the alternative value. Now, freeze for just a second. Notice there's something you don't have here. Okay? You don't have an X bar. There's actually no sample that's been taken yet, and you don't need one, right? This calculation is saying if I'm sampling from this curve, right, what are the chances that I land over here in this other curve, in this beta region, and say, oh yeah, things are great, when they really aren't great, okay? So that's what we're doing. There is no actual X bar. It's just like when you do a calculation on margin of error and you're solving for n, right? You don't need an X bar. All right, so step 1, what's a type 1 error? Well, type 1 error is simply alpha. Easy peasy. Okay, now the next step is we have to figure out, okay, when is it that we're going to be rejecting the null hypothesis? Okay. Well, if alpha is 5% and you're doing a one-tailed test, you just got to get your z-score where 5% is, in this case, on the right. Okay, so get your z-score. Looks like this. Right, so you can look up 0.95 in table A, or you can do an inverse normal. I always just go for the inverse normal because it's a little more accurate, right? So there's your z-score. Anytime you are that many standard deviations for above the mean, you would say, our machinery is making defective ball bearings, shut it down. Okay, that may or may not be true, right? It might be that it was just random chance, but that's the cutoff for deciding if you're accepting or rejecting that null hypothesis, if you're shutting down your machinery or not, in terms of z-scores, right? In terms of standard deviations. Okay, which I think is on our next slide. Yep. Okay, so there's the z-score that we just found. Okay. All right, now, when we actually are doing our significance test, trying to decide, are we shutting down or not, right? The null hypothesis is everything's great, 2 centimeters. The alternative is, no, they're too big, okay? And what you would be doing is you would be calculating your z-score like this, right? Whatever your sample mean is, you'd say -2, the null hypothesis, over the standard deviation, right? And whenever that right there exceeds this z-score, we would shut things down. So that's the cutoff, okay? So that's what we got to do. So set that equal. Oh, now the whole inequality, a lot of you are like, wait a minute, the inequality, how do I know? It actually doesn't really matter, right? Because one direction gives you type 2 error, the other direction gives you the power, right? Again, think back to that diagram, right? Okay, so you have some cutoff here, and right over there is one error, and over here is another error, right? So as I flip-flop, I'm just flip-flopping between a correct decision and an incorrect decision if I'm on this curve, right? So that right there, that beta area, that would be your type 2 error. If I flip it the other way, then I'm finding the power. All right, so anyway, solve this for x bar. Right now, we're in terms of this 1.645. That's how many standard deviations above the mean I need to land in order to shut down my machinery, right? That's the cutoff for making that decision. Well, I want to know not in terms of standard deviations. I want to know in terms of actual data and actual x bar. So solve this for x bar, and we should get this. Okay. So this mean for the 5 ball bearings that I sample is the determining factor if I stop the production run or not. Okay, whenever X hits this in one direction, I shut it down, right? If it's above this, I shut it down. If it's below this, I keep the production run going. Okay. All right, so now it's time to do. So in other words, that was actually just an inverse normal calculation, right? I could have done this just to show you. Inverse normal, okay. 0.95, and then I would put in, what was the number? 2 and 0.01 divided by square root 5. So that's how we got it. So that's the first half of the calculation. It's just an inverse normal. You're just trying to figure out what's the cutoff in terms of my sample, right? Where is it that I'm going to be, making that decision? Where's that line in terms of the sample value? Okay, now I go back using that, but, okay, I'm saying I'm on the other curve. So what are the chances of hitting this value if I'm on the other curve, right? That second curve. Okay. So I found that this x bar, well, first I have it as a z, right? Z star. Then I convert it to an x bar. Okay. And now I'm going to say, if I'm on this curve over here, what's the chances of landing over there or over here? Doesn't matter again. Type 2 error or power, depending on which side you're looking at, okay? So I'm on this curve. This is actually, we're saying now is the true parameter, and let's plug that in for my x bar. So there we go. And when we solve that, that's what we get. So for this situation, the power of a type 2 error is about 4%, right? You see, because this over here, this is the type 2 error, right? We're saying we're on this curve. This is the mu equals 2.015, right? We're on this curve. The chances that we land over here and keep the production run going when I should be shutting it down, it's right there, 4%. Okay. Now, if I flip the inequality around and say greater than, right, then I would have my power. So my power is simply 1 minus that. And there you go. That's how we calculate type 2 error or power. Just flip that inequality. Okay, so the calculation, just to briefly run it down, it's an inverse normal calculation to find the cutoff in terms of x bar. Then it's a normal calculation using that x bar that you calculated and the alternative curve. So it's kind of just two calculations in one. That's all it is, but you know, obviously two calculations is, I guess, twice as hard, twice as easy to mess up. And of course, you have the two different mu's. You had the mu of 2, and then the alternative mu of 2.015. So a lot of times students kind of get messed up there. Let's do a quick question. This is something that you might be asked on the test, right? In context of this ball bearing problem, what would constitute a type 1 error? Right? In context of the ball bearing problem, what would constitute a type 2 error? Okay, so think about that for a second. Pause it, see if you can answer it. So a type 1 error, go back to my diagram here. A type 1 error would be, I'm on this curve, I'm actually making good ball bearings, but for some reason, I just got a really rare sample over here, and I said, oh, shut it down, stop making ball bearings, recalibrate, right? Throw out that production run, they're bad, even though they actually weren't. So that would be a type 1 error. Shutting down my production when I shouldn't, disposing of perfectly fine ball bearings because I thought they were defective. Okay. Now, type 2 error. Type 2 error is I'm actually off calibration. My machines are now calibrated off by 0.015 centimeters, too large. But I got a random sample that lands over here, and I think everything's great, and I keep making more ball bearings, even though I should be shutting them down. Okay? So that would be the type 2 error, accepting defective ball bearings. The type 1 error would be getting rid of acceptable ball bearings. Okay. Now, I might do a follow-up question and say something along the lines, which of those two errors is worse? Okay. And again, you would need a little more context probably, right? If these ball bearings are being used in some really cheap, like McDonald's value meal toy or something that, you know, the toys break anyway, I guess it wouldn't be horrible to throw in some ball bearings that are not so good. But on the other side of the coin, what if these ball bearings are being used in, say, jet engines on airplanes? Now, the type 2 error would be potentially catastrophic, right? So the type 2 error in that situation would be really bad. You have to read the context of the problem, but I will certainly have context of the problem enough in there that you could say, you know, type 2 error is worse or type 1 error is more severe. So that's something you should be able to do. Okay, so there you go. Oh, side note, when you are trying to get funding for, say, government research, right, they will set forth, oh yeah, you need an alpha of whatever, and you need a power of at least 80%, right? Those are the most common alpha is 5%, the most common power is 80%, which is kind of scary, right? Type 2 error 20% of the time, but those are the common research criteria if you're trying to get government funding. So just a side note. And again, just to follow up what I said earlier, you start with your inverse normal. You use your inverse normal to get your x value, right? If you're doing two-tailed, you'll be getting two x values, a lower bound and an upper bound. If you're doing a left tail, then that. Doing a right tail, you only have, again, one. And then So the inverse normal will give you this bit. Okay, so this is from the inverse norm. Okay, and once you do the inverse norm to get that information, you then just do a normal CDF using your new mu. And there you go. That's how it works. So good luck. Make sure to study that. And make sure you're ready for the test.